Hello and a very good day to our lecturer. My name is Ponchin Phai with a matrix number AE190091 from Group 2 of Section 2. In my segment of the video, I shall be giving a brief presentation on the introduction and Part A of the PBL2. Firstly, I shall give an introduction to PBL Activity 2. Modulation is the process of altering one or more properties of a periodic waveform known as a carrier signal with respect to the modulation signal, which contains the information to be transmitted. Modulation is performed by the device known as a modulator, and the technique is mainly used to overcome the interference of the signal, where modulation techniques usually assist in long-distance communication, as they can go quite far. In the case of problem-based learning activity 2, pulse code modulator circuit digitize the given analog signal, codes it and samples it, then they transmit it. This entire process can be repeated in a reverse pattern to obtain the original signal. However, the encoding and decoding process must meet certain crucial requirements, including sampling frequency, quantization, interval voltage range, and allowable amplitude modulating in certain ranges. Pulse code modulation techniques are used to produce a series of numbers or digits in binary form. Hence, the process can also be called as a digital modulation. The amplitude at a particular time of the signal sample is indicated by the binary codes. The pulse code modulation process is done in 3 steps: sampling, quantization, and coding, in a general way of explanation. Other than that, pulse code modulation is usually used in satellite transmission systems and space communications. Now I shall present Part A of PBL Activity 2. Since MT is given in the activity, which is MT is equal to 5 sine 2 pi 100t, hence according to the Nyquist criterion, Fm over here would be 100 rads per second, which comes out at around 15.915 Hz. Hence, the sampling frequency Fs would be 2 Fm. So Fm, we know that is 15.915 Hz. Hence, the sampling frequency Fs would be 31.031 Hz, around that value. So the period for the sampling frequency, T is equals to 1 over F, so 1 over that would be 0.031416 seconds. Now heading over to the 4 bits encoded PCM data, as we can see from this figure, the signal is converted into the digital form through pulse code modulation at a bit rate of 124 bits per second, or bps, 124 bps, and at a bandwidth of 124 Hz. And as we can see in this figure, shows the modulating signal after it has been encoded and decoded using the pulse code modulation at 4 bits. So over here we have the 8 bits encoded PCM data. From this figure, the signal is converted into digital form as shown in the 4 bits encoded PCM data. It's about the same through pulse code modulation at a bit rate of, there's a different bit rate of 248 bps, or 248 bits per second, and at a bandwidth of 248 Hz. And it seems that aliasing is at work and in effect, as shown by these lines over here. And over here, down at the right corner, the figure here shows the modulating signal after it has been encoded and decoded through pulse code modulation at 8 bits. Alright, that is all from me. Thank you very much for watching.
Alright, very good morning to all lecturers who's watching this video presentation today. My name is Legend Zero. I'm from Group 2 Section 2, BEV30103. Now I'm going to present you about the PBL2 for the Part B section. So since MC equals to 5 sine 2 pi 100t, hence according to the Nyquist criterion, Fm equals to 100 Hz, and also Fs is greater than 2Fm. Multiply 2Fm with 3. So sampling frequency Fs equals to 6Fm, 6 times 100 which is equals to 600 Hz. The period is 1 over frequency, which is the 0.001667 second. And for 4 bits encoded PCM data, as we can see from the figure above, the signal converted into digital through a pulse code modulation at a bit rate of 382 beat per second and a bandwidth of 382 Hz. Here is the figure that we get from the simulation apps. And next, here is also the graph here. So the figure above show the modulating signal after it has been encoded and decoded using a pulse code modulation at 4 bytes. Okay, here. Next is a 8 bytes encoded PCM data. So this figure is the signal converted into digital through pulse code modulation at a bit rate of 764 bits per second and a bandwidth of 764 Hz. And it seems that aliasing as at work and in effect. This is both. So from the figures above show the modeling signal after it has been encoded and decoded through pulse modulation at 8 bits. This is encoded and decoded. So this is all from my part B. Thank you very much. Thank you for your attention. Next, it will be left to my teammates to explain with you for the next part. Thank you very much.
Assalamualaikum warahmatullahi wabarakatuh dan selamat sejahtera. My name is Nurshahani binti Abdul Halim, AE190045, and I will present you about the part C in PBL2 assignment, digital communication, chapter 4. Okay, for the question that given, the scenario, sampling for MT is lower than minimum required according to an quiz. And sampling frequency Fs is lower than 2 FM and n bit encoded PSM is 4 bit. Okay, for this we choose to do the simulation like this. Okay, for the we want the encoded graph at here. Oh, sorry, wait. I will show you how to put this. Okay, for the frequency I put 15 and 100. F15, sorry, 50 Hz. Okay. And the impulse signal, I put this period, time. Okay, for the result, run this project. Okay, to see this, save with our report like this. Okay, larger than this same. Okay, for the oscilloscope, signal at the scope like this. Okay, same with this. Okay, for the report we can see the signal from pulse concentration evaluate 60 bps because 4 times 15 is 60 Hz and bandwidth equal to BR. Okay, by rate, and tadi tengok, okay, the figure tu the waveform of modulated signal and is encoded at 4 bit. Okay, that's all for me. Thank you.
Good afternoon, my name is Suzy Sam. My meeting number is AE1900912 from Group 2 and Session 2. Today I'm going to discuss about the Part D of PBL Activity 2. So the first question of the Part D is going to ask what happened to the resultant recovering modulating signal M prime T M prime bracket T. So if the amplitude change to the 15 volt and 0.5 volt, so we can see that this is a waveform for the 50. This is a waveform for the 50 volt, and then there also waveform. We do 2 bit. One is 4 bit and 8 bits according to the part B. So we do 2 bit. So these are 4 bit for the 15 volt, and then this is a 5 bit. This is a 8 bit for the 15 volt. So next we do the 0.5. So we can get the result of this. And then 8 bit also we also do for the 0.5 volt. So this also the 0.5 volt for 0.5 volt for the 8 bits. So this is a 4 bit for the 0.5 volts. So next, by analysis the waveform of the resultant recover modulating signal from 4 bit and 8 bit encoded, the signal of 0.5 amplitude is smoother than the 15 volt amplitude. So we can see that they are smoother. We can see that 15 volt. You can see that 15 volt is not smoother. You can this is not smoother. So we can see that 0.5 is smoother than the 15 volt amplitude. Since Vm equal to the 0.5, the step size and quantization error decrease. Therefore, the shape of the signal becomes smoother and more accurate. Next question is going to ask about what will you suggest to make sure the M prime bracket T is similar to the M bracket T. So we just add the, so based on the part D, we use the amplitude 0.5 because we just discussed 0.5 volt is smoother and more accurate than the 16 volt. So we use 0.5, and then the other volume of the block same as the previous, and then we add on the gain from the figure. So we can see that from figure above we can see that there again we add on. So to smoothen the waveform of the resultant recover modulating signal. To smooth again in order to become more accurate as the resultant as the M bracket T. So this is a waveform of modulating signal M bracket T. So we can see that they are same already. So we can this is a M prime bracket T. So this is a resultant recover modulating signal. So from figure both, so we can see that there is a similar between them. So our method by adding the gain has been proved to use this method to make the resultant recover signal M prime T which is similar to the modulating signal M bracket T. So this is all for me. Thank you.
A very good day to doctor. My name is Tenaganifa, AE1900077. Today I'm going to do a presentation on BEV30103 Program-Based Learning Activity 2. So I'm going to do Chapter 4 Digital Communications with MATLAB simulink of using this modulating signal. So we're going to construct it, and we're going to do scenario 1 until 5. So based on it, I'm going to start my discussion. So what is a pulse code modulation? That is a type of digital to analog conversion with information contained in analog signal samples is represented as a digital words in a stream of words. And then the encoding and decoding process involve a sampling frequency, quantization, and amplitude modulation range. So in part A, that we are going to calculate our step size in the scenario 1, which is a 4 bits encoded, and scenario 2 also as well with 8 bits. So we're going to see that the sampling frequency is equal to 2 times the maximum frequency. So based on our graph obtained from the MATLAB Simulink, that we can see that our output signal is 8 bits is higher than 4 bits. So which is 8 bits is a high level signal and 4 bits is a low level signal. So in our part B, we're going to do a sampling frequency is larger than the 2 times of the maximum frequency. So as long as the sampling frequency is larger than the maximum frequencies, so that they will not have a zero, the gap will be smaller and they will have non-zero separation. So it is possible to recovery in our questions that we're going to recover the resultant modulating signal from the to the original setting. Okay, so in our case we are using 4 bits, so we have a 15 levels, 0 to 15. So binary code is from here until 16 until the 2 power of n, which is 4, so we have 16 levels here. So in our part C, that what we're going to do is sampling frequency is less than true maximum frequency. So we can see as long as this is less, so it's not enough. Hence we can reckon that recovering of a signal is not possible. Okay, so for part D, then we're going to have our VM amplitude of the modulating signal is equal to 15 and 0.5. As you can see that if this is equal to 15 volts amplitudes, then the quantized area and the step size will increase. Therefore, the gap will become larger, and it's hard to change it back to the original signal. So, on the contrary, that if 0.5 volts, the step size is smaller and the quantized area will decrease. So, it is possible to recover it. So, in our recommendation, that we are using the GAN block and the low pass filter block to accomplish the recovery of the modulating signal to its original signal. Thank you.